Oh, hi. Welcome to pre-lab lecture on Titrimetric determination of chloride in a known sample. I'll walk you through the calculation. I believe you have collected the data, and this lecture recording is meant to walk you through the calculation. Allow me to share my screen. I will walk you through the calculation all the way through determination of mass percent of chloride in a known sample. What you see now is my whiteboard. I'm gonna have the data sheet or lab notebook organization as well as the procedure. Now, these are the three main section in the lab: preparation of 0.05 molar silver nitrate. I gave you a sample which you dissolve in 1 liter glass topaz bottle, and then standardization of the prepared 0.05 silver nitrate and the analysis of the unknown. I'll have another document that is the notes and how to proceed with determination of the mass percent. So at the outset, this is how you prepared your solution. In part A, I'm going to break it into two, part A and part B. Part A, standardization of around 0.05 molar silver nitrate solution, which you prepared in 1 liter class stopper bottle. The silver nitrate I gave it was around 5.3 grams. You cannot use this mass to determine the concentration of the prepared solution. You will need to standardize using the primary standard, which was sodium chloride. You should have the purity factor so that you use that to do it, to calculate the actual mass of silver chloride in each sample. So you had to weigh 4 samples in different flasks. For sample in 500 ml flask, we call sodium chloride primary standard, which we use to standardize silver nitrate, which will be the titron in part B analysis of the unknown. This was the suggested, or this is the suggested mass for the sample, which you had to weigh by difference. By now, you should know what this weighing by difference is. You just weigh the bottle, that's the weighing bottle, plus the sample, and then you transfer anywhere between 0.1 and 0.2 for your chloride, and following the instruction, you dissolve, and you had to do what? You had to titrate to end point. So we assume that this is silver nitrate here. This is AgNO3, which is unstandardized. Depending on which period you are using, either period A or B, it should be calibrated. You should have a calibration curve for either A or B. Trial 1, trial 2, trial 3, follow the instruction how you had to dissolve each sample. And let's see, if you titrate each one of them to endpoint, trial 1, trial 2, trial 3, you should have the masses of each. Let's say mass of each sample based on the lab notebook. Lab notebook, you should have the data sheet or lab notebook organization. If you look at trial 1, you had the file plus the sample, you transfer 0.1, your final mass will be file minus the chloride, which went into flask number 1 for trial number 1. Pay attention to sodium chloride apparent. This is what you recorded when you find the difference between the file and file minus the chloride, which went into 500 ml flask. Purity factor, the purity factor was 100 purity factor here was or percent assay here. Percent assay, let's see here. Let me just minimize here so that I can write here percent assay. Is 100.03%. You need to record this value in your lab notebook so that you derive the purity factor here. Okay, purity, and to put here purity factor is 0.10003. This is the purity factor you need to put in your lab notebook so that when you multiply the purity factor here by the apparent mass of sodium chloride for each trial, you get the actual, all right? Here, actual and ACL is apparent times purity factor. All right, this will give you the actual mass of sodium chloride. So when you see this value here, I need to see the actual mass. Show the calculation. How do you get the actual mass of sodium chloride? There's a difference between apparent and actual. This is just the raw data when you weigh out or mass out the suggested grams of sodium chloride before you treat the data using the purity factor. You will perform the titration for each trial 1, trial 2, trial 4 using, look here, using either purette A or B. If you're using purette A, all right, indicate the purette here if it is A or B. You need to have the calibration curve. Remember experiment 2, you had to calibrate both purettes. Even though I recommended that you can move forward with calibration of one purette, in experiment number 4, you will need both purettes calibrated. So if you calibrated A, you'll indicate A here. If you calibrated B, you will use B as your purette for titration. This is titration of the standard, which is sodium chloride. And let's say your initial volume on the purette is 0, okay? Your final reading may be, let's say, 30. 30 minus 0, it will give you apparent volume. So if here is your endpoint, all right, let's see your endpoint from this titration here. If you started from 0.00 ml and finally started 0.00 ml, this is initial and this is final. So apparent volume is 30 minus 00 minus 0.00, which is 30.00 ml. You will go back to a calibration curve for purette, either A or B, and let's say this is calibration curve. It can be going this way. You'll have to see where 30 is and use the correction factor on y-axis. It could be positive for your case, that's fine. It could be negative, so that when you plug in the value here in titration, see titration, this is the titration initial 0.00 based on the illustration, and final is 30.0. I'm just giving you hypothetical numbers. When you subtract final minus initial, you get what we call apparent ml. I know in lower level chemistry lab you took, it didn't really matter the correction of or the volume error from the calibration curve. There is plus or minus here, which means, let me just blow this up. These plus or minus here, some folks, they have their calibration curve on the positive territory. Some folks, they have their volume correction on the negative territory. So you have to apply the correct sign from the calibration curve. So here, this is from what? Calibration curve, all for trial 1, trial 2, trial 3. I don't know what your final is. So apparent is when you subtract. You use the calibration curve to get the actual. This is the actual when you subtract the volume correction from the calibration curve. So it's important to take into account the volume error from your calibration curve. By now, you should have that. Once you have that, the next thing is to determine the molarity of your prepared AgNO3 silver nitrate. Remember, you did 4 trials, and we need to find the molarity. To get the molarity, all right, to get the molarity, it's given, or you will use this equation. Let me just go back and see. There is an equation here which you need to understand how it is used in determining the molarity of silver nitrate. This is the chemical equation representing reaction between number of moles of sodium chloride with number of moles of silver nitrate. It is 1 to 1. This is in the flask. This is the titration in the puree, and the mole ratio is 1 to 1. What this equation? This is the molarity of silver nitrate, which is the same as this equation I have here. This right here is, I need to label this. This is the grams or actual grams of silver, sodium chloride for trial 1. This is trial 1. Molarity of AgNO3, all right, for trial 1 is grams for, that is the actual grams of sodium chloride, times the mole, using the molar mass as a conversion factor for millimoles, all right. You'll use all the significant figures given in this equation. Please do not round off 1, 2, 3, 4, 5. Okay, 5 significant figures. Mole ratio, the last one here is the mole ratio between sodium and silver all over the ml of silver nitrate used. Look at the over, everything over. Okay, this is at the top, and it's important to understand that the denominator is the silver nitrate used to titrate the sample to endpoint used in titration. All right, and this is actual as well. Actual meaning you have to take into account what? Into account the volume correction. If I go back to the data sheet, right here, this is the volume of silver nitrate. You'll do this for trial, this is trial 1, trial 2, you do the same thing, trial 3, and trial 4, calculating the molarity for trial 1, trial 2, and then molarity of AgNO3 is given by of 3 you discard one, which is you treat it as an outlier. So I'll use only 3 which are precise to find the molarity of prepared silver nitrate, which you will now use as your standard in titration of a known sample. Each individual was assigned a known sample with different mass percent of chloride. That is the objective of this lab, to know or to determine the mass percent of chloride in your assigned sample. The instruction called for weighing between 0.120 grams to 0.1500 grams of a known weighing by difference. You're familiar with the technique by which you weigh each, don't place LML flags on analytical balance. You're gonna weigh for measure out or mass out for samples, follow the procedure outlined here to get the required mass. You dissolve in the suggested ml of the ionized water, add the dextrin in the indicator, and proceed with what? With the titration until you determine the endpoint. Let's say this is trial 1, trial 2, trial 3, trial 4. All right. Either calibrated period A or B. I'm using these numbers to represent, okay, the titration values for period A or period B. Look at trial 1. If this is trial 1 or this trial 1, assuming that the initial is 0.00 ml, 20.00 ml, this is final. Let's say here, final. This is initial. All right, final, initial. You will use the calibration curve. Still, you need to do what? Indicate the rate you are using. If it is A, you have to indicate A. Final volume from this illustration, final volume to see the endpoint based on the color change. Initial volume when the meniscus was titrate. Pay attention to the apparent volume. In this case, apparent volume is final minus initial, final minus initial 0.00 ml. I have 20.00 ml. So this is apparent right here. This is apparent. Now, actual is you'll have to look at the calibration curve. So if this is calibration curve going this way, you have to look at where 20 is. If this is 20 right here, 20.00, what is the correction factor on the y-axis? This will be ml is 20 correction from the calibration curve. What is the correction or volume error from your calibration curve for either period A or B? This will give you the actual ml of silver nitrate, which we are going to use now to determine the mass percent of chloride in your assigned sample. So be careful. There is the apparent ml of silver nitrate, and then there is the actual ml of silver nitrate. This positive, negative, it depends on which territory your calibration curve is. And once you have that, you are ready to determine the mass of chloride in the unknown sample. Let's use trial 1 as an example. You'll use the equation here, right here, this equation given in the handout, grams of chloride in an ensemble. This is the actual, by the way. This is actual ml of AgNO3, not the apparent, the actual. Once you treat that, and then ml or millimole of silver nitrate, ml of silver nitrate, so that you can cancel this and cancel ml, millimoles of silver nitrate, millimoles of silver nitrate, millimoles of chloride, millimoles of chloride. This will give you the grams of chlorine or chloride in your unknown sample. Let's just put that chloride or chlorine is the same thing. Okay. This is trial 1. You will do for trial 2, trial 3, trial 4, trial 1, trial 2, trial 3, and trial 4. And remember, the units will be in grams. So this will be in grams, trial 1, trial 2, trial 3. Remember, what will come here is, the average. This is the average molarity. This is the average molarity from the previous section. The average molarity of silver nitrate. Now, the mass percent now, mass percent of chloride ion or Cl in your sample, let's say trial 1, you know how much of the unknown sample you had in trial 1. You should have in your lab notebook mass of unknown in trial 1, mass of unknown in trial 2, mass of unknown in trial 3 times 100. Actually, this is the equation to get the mass percent. Analyte is the chloride. This is the analyte right here. It is the chloride ion, or just same as chlorine or chloride, it's the same. You will fill in the lab report form for mass percent for trial 1, mass percent for trial 2, trial 3, and trial 4. And just like in experiment number 1, you will report the mean, okay, the standard deviation and relative standard deviation. You will see on the folder on Canvas what needs to go in the report form for this lab. Other than that, thank you.